Consider the hypothetical reaction, where 2 moles of A gas yields 1 mole of B gas and 3 moles of C gas. Suppose a fixed volume container initially holds 2.00 moles of pure A at a pressure of 0.500 atmosphere. Then, hours later, the pressure at the same temperature is found to be 0.800 atmosphere. How many moles of B are present in the final mixture? Since this problem involves gases, let's see how we can use the ideal gas equation to solve this problem. We know that in this equation, R is constant. The problem tells us that the reaction occurred in a fixed volume container and that the final mixture is at the same temperature as the original gas sample. Therefore, for this particular problem, the volume and the temperature are also constant. Let's rearrange the ideal gas equation so that all the constants are on one side of the equation. If we do that, we get P over N is equal to RT over V. Note that the right-hand side, RT over V, is a constant, since RT and V are all constants. What this means is that even though the pressure, P, and the number of moles of gas change in this problem, their ratio is constant. P over N is equal to a constant. When the ratio of two quantities is a constant, we say that they are directly proportional. This means that in the case we have here, pressure is directly proportional to the number of moles of gas. The more moles of gas we have, the higher the pressure. In other words, the increase in pressure is given in the problem, from 0.500 atmosphere to 0.800 atmosphere, is due to an increase in the number of moles of gas as a result of the reaction. We can see from our balanced equation that every time we lose 2 moles of gas A, we are replacing it by 4 moles of gas, 1 mole of B, plus 3 moles of C. The moles of gas will be increasing as the reaction occurs. We have enough information here to figure out the final moles of gas. If we refer to the initial pressure and moles as P1 and N1, and refer to the final pressure and moles as P2 and N2, then we know that for this particular problem, where V and T are constant, P1 over N1 must be equal to P2 over N2. We can rearrange this equation to solve for the final moles of gas. The final moles of gas, N2, is equal to the original moles, N1, which is given in the problem as 2.00 moles, times the ratio of final pressure to the original pressure, P2 over P1. P2 is given as 0.800 atmosphere, and P1 is given as 0.500 atmosphere. Performing the indicated calculation gives us that N2 equals 3.20 moles. The total number of gas molecules in the final mixture is 3.20 moles, but the problem is asking us for final moles of B. What we have at this point is just a stoichiometry problem, twisted a little bit. We're not given explicit information that we can use to easily figure out the change in the moles of reactant or any one of the products. This suggests that we have to use algebra to represent our unknowns. The basic idea in stoichiometry is that the amounts of reactants and products that are consumed or produced in a reaction are directly proportional. This means that the mole-to-mole ratio of any pair of substances involved in a reaction is constant, and that constant is simply equal to the ratio of their coefficients in the balanced equation. For the reaction we have here, where the coefficients of A, B, and C are 2, 1, and 3 respectively, if 2x moles of A were consumed, then x moles of B must be produced, and 3x moles of C must be produced. Regardless of what the value of x is, the mole-to-mole ratios are constant. For example, the mole-to-mole ratio of A to C will always be 2 to 3. Moles of A divided by moles of C is always equal to 2 over 3. The variable x that we're using here is called the moles of reaction, our extent of reaction. At this point, we have enough information to set up the algebraic expression for the final moles of A, B, and C. For reactant A, let the final mole be N sub A. This is equal to the original moles, 2.00, minus the amount consumed, which is 2x moles. Similarly, the final moles of product B is N sub B. Then N sub B is equal to the original moles of B, 0, plus the amount produced, which is x moles. As for product C, the final moles N sub C is equal to the original moles of C, 0, plus the amount produced, which is 3x moles. Therefore, the total moles of gas in the final mixture, which we earlier represented by N2, is equal to the final moles of A, plus the final moles of B, plus the final moles of C. This expression can then be simplified to 2.00 plus 2x moles. Recall that we earlier found the total mole be 3.20 moles. Therefore, 2.00 plus 2x equals to 3.20 moles. Solving for x gives us a value of 0.600. So now all we have to do is plug in x to calculate the final moles of A, B, and C. The amounts of A, B, and C in our final mixture are 2.00 minus 2x, or 0.800 moles of A, 0 plus x, or 0.600 moles of B, and 0 plus 3x, or 1.80 moles of C. Therefore, the correct answer to this question is 0.600 moles. The number of moles of B in the final mixture is 0.600 moles. We can do one final check to verify that our answer is correct. The total moles of A, B, and C should add up to 3.20. Indeed they do. 0.800 moles plus 0.600 moles plus 1.80 moles equals 3.20 moles.